A while ago, we obtained there is a question about the example on page 7. 7. Page 7. Okay. Here, right? This one? This one? Can we obtain the result by symmetry? I think you can obtain some idea about the answer by symmetry, but you cannot obtain the detail, for example, the coefficients, all that kind of things by symmetry. Get me? All right. Okay. Now, by that I mean it is not entirely by symmetry, but it is more by, it is not symmetric. You understand what I'm saying? Okay. Now, first of all, a good idea will be to try a guess. What is the form of the ground state, for example, right? So with such a thing, it is reasonable to think that the particle will spend more time, well, more probability to be found on this side. Okay, do you follow me? There's a question from the student. Okay, follow me? Because it's lower energy, lower potential energy. All right. So therefore, you will expect some wave function that is tilted to the other side instead of symmetric about the middle. Do you follow me? Is that okay? Is that okay? Now, you start off with the ground state wave function with the symmetric in the middle. If you keep on adding the other symmetrical one, you will never tilt to one side. Okay, do you follow me? Okay, therefore, at the end, the results tell you, don't add those up. Those do not contribute. Only the one that has a positive, negative, more positive on one side would contribute to you, so that you can decorate the ground state towards what you expect. Okay, so I think that is how you make use of this physical sense. Now let me continue on with our matrix math discussion. So we know what first order is. Look at the diagonal element. What second order is? Focus on another one, effect on you, take that out 2 by 2, okay? And if the energy difference is bigger than the coupling of diagonal, simply use 2 by 2 approximated form, and then you get second order energy, okay? So now, the next question is, what if after we read out the 2 by 2, the unperturbed energy that appears in the diagonal elements happen to be close to each other or even the same? All right? Then what to do? We shouldn't use this approximation form, delta squared divided by the energy difference, because that relied on an expansion of the square root. What to do? The answer is not to do anything, right? Meaning not to take that square root expansion. You just do the 2 by 2 exactly. Everybody can do it, right? So that happens to be something important. that is called degenerate perturbation theory. I hope that now you understand the name. The degenerate, this word means in the unperturbed situation, for a particular energy En, for example, there are other unperturbed energies that are close to this energy or even equal. Now, that is degeneracy. But actually, you don't need to wait for two eigenvalues to be exactly equal. When you are sitting on N, you find something that is already near to you. There is a warning flag. Be careful. Okay? Right? So now, this theory, in one line we can work it out, is called degenerate perturbation theory. Sounds very profound. But if you understand what we have been doing, you will see that that is easy. It's a byproduct, okay? Nothing kind of a separate part. No, it's just an integrated part. We just do it. We have to take care of another situation. That's the form. That is the point. So we saw in results non-degenerate perturbation theory this kind of expression. So when the denominator becomes too small, okay, this is smaller than delta, okay, not square, just one of them, okay, then be careful. Don't make the expansion on the square root in the exact expression. So now we do the same thing again. The situation is that you sit on N. Previously, you are asking for something, I or K, the effect on you. We realize that the unperturbed energy difference, this one, is bigger than the coupling, the delta, or the H prime and I. Then we can comfortably make use of the expansion in the square root in the quadratic solution. Now, when you see this kind of situation, you are here, you see a nearby state. The energy is close to you. Be careful, right? Okay? But before we do anything to the 2 by 2, we have to read that out, right? So after we read out the 2 by 2, it's still the same form. Nothing new. I may have energy very close to N. Nonetheless, all these are the same, so this is still fine. Write it out more explicitly. The diagonal matrix element has to do with the zeroth order and the first order correction. So this is the form you need to handle. The problem is to solve for E. Do it. It's quadratic. I just copy result. You do it this way, stop there, then you are doing degenerate perturbation theory because you haven't assumed anything about this difference against this energy. Up to here, everything is general. That can be big, that can be small, that can be big, that can be small. All right? Get me? Okay. So I'm assuming in this expression, the zeroth order unperturbed energies are exactly the same. All right? So I have only one value here. Get me? So there's nothing fancy, and this result happens to be called degenerate perturbation theory when you have N and I states with degenerate zeroth order energy. You may wonder, what happened if I have 3 states that are degenerate in H0. That happens, right, in atoms. Px, Py, Pz have the same energy, say 2p. You apply a field, what happened, okay? Something like that. Now, when you have three energies that are degenerate or very close to each other, then you should read out, instead of 2 by 2, separately, this group of three nearby energies should be treated together. So you read out a 3 by 3, 9 matrix element, and do that part carefully. Don't make too much approximation. Then you are doing degenerate perturbation theory again. Okay, so it is just as simple. Now let's look at some physical effect. Usually, you apply something, H prime, to the system that has degenerate states. That is to say, without this, they are the same. Okay? Now, you apply the perturbation, what happened? You look at this final answer, there's a plus minus, meaning as you crank up the H prime, the effect, try to mix them, they will split into different energies, right? One is going up, one is going down as the strength of the perturbation increases. We have a term for this. We say this perturbation is removing or leaping the degeneracy, okay? Removing is easy to understand, but there is a jargon called leaping the degeneracy. Using a coupling or an interaction represented by H prime here, okay? It is easy to see from the result, obvious. So I mentioned this situation. If you have three states in the unperturbed problem that are degenerate, what can I do? Don't worry. Read out that part, the whole thing, and then do that part more carefully. Okay? An example for this problem is later on, we will consider something called spin-orbit interaction in an atom. So in an atom, you will have p states that are degenerate. Okay, so L equals 1 is p. So you have y11, y10, y1 minus 1, the spherical harmonics. They are degenerate. But now if you include a effect called spin-orbit interaction or an external field called Zeeman effect, then that will split the degenerate state into different energies, okay, as a result of your extra term. Here is an external B field in this example, okay? Now, one remark, for those who have learned some linear algebra, better matrix mathematics, a reminder is the following. Okay, now, for those who are not familiar with too much matrix mathematics, don't worry, okay? Don't worry too much. At the beginning, we have a big matrix. We are saying that if you see some diagonal term that have similar numbers in H0, read that part out and do it carefully. This is a description of the following mathematical action. You read that part out, try to change the basis so that this part becomes diagonal. So you do it exactly, that is the same. Now, after that, you may ask, the other states out there that I haven't focused on should still have some effect on my eigenvalues. Second order pushing. They must be there, right? I first focus on that group, but there are others, okay? Then the mathematical thinking is that after you do this part exactly, you are changing the basis for this three. You put it back, okay? And then you have to change the matrix elements of the others because this particular group has changed the basis. Thereby, you can rewrite the matrix and then use the non-degenerate way to get the second order correction coming in. Again, okay, using this approximation 2x2 approximation. And that is sometimes you need to do it, especially in solid state physics. So this is what I just mentioned, okay? But this is optional, it's deeper, okay? For those who are comfortable with linear algebra, I hope that you get the idea. If not, don't worry. So let's take stock. We are done with approximations part one, okay? Later on, there are a few more approximation tricks we will introduce when the context comes. But at this point, we have a few good tricks. We can write Schrödinger equation exactly into a big matrix that is exact, not approximation. I hope that you already sense that is the foundation for us to think about many other approximation schemes. We talk about variational calculations, especially when the trial wave function is a linear combination of several functions. That can be related to the big matrix, but in an approximation way. We're truncating that matrix into a smaller one. Then we derive formally first and second order correction in perturbation theory, and the result tells us it is non-degenerate perturbation theory. We also get the first order correction to the wave function. Then we understand these results using the big matrix, ignoring all the off-diagonal element. It is first order in energy, taking another state in, looking at 2x2 separately, many 2x2 repeatedly, we get the second order correction in energy. In doing so, we also discover when the diagonal elements are close in zeroth order energy, be careful. Do it well, do it exactly, and that happens to be degenerate perturbation theory. So we have all these tools now, and now it is time to make use of that in various contexts. We will do atomic physics, some physics of atoms, not the whole subject, of course. We will do some physics of molecules. In these two subjects, you will see that we will make good use of all these tools. Okay, I already hinted at when we discussed the 2x2 matrix. You have a state here from atom 1, you have state here from atom 2, come together, they form bonding, anti-bonding. Push down, push up. That is the Hamiltonian matrix mathematics. Okay, so we are done with this part. Okay, so I will pause to see whether you have questions on all these tools to move on. Okay, any questions? We are done with part one. Page 21. This one? Okay, so are you asking why this? Is that the question? Okay, now remember what we are focusing on, degenerate perturbation theory. That means the following. In your H0 problem, there are some degenerate states. Okay, so do you understand this statement first? That means there are two states, at least two. There may be three, there may be four, but at least two states, they have the same energy in H0. You understand me? So now I want to study when the n state I'm considering has another I that has the same energy. So I use this special case. Therefore, the zeroth order energy are assumed to be the same. Get me? Then I do this thing exactly. It's quadratic in E. So I copy the quadratic result previously. I got this. It so happened that even Griffiths give this result and then call it degenerate perturbation theory. But you see, it's nothing, okay? Why then it's not? Okay, because the wave functions could be different, right? It should be different. Do you understand? Now, what is this? This is H prime in the middle. And then psi n0 star psi n0 and do the integration. You understand me? But when it is state I, this thing become I. Do you see? Different wave functions. That is the definition of degeneracy. Do you see? Different wave functions, same energy. So there's no guarantee the integrals of H prime of the two different states to be the same. There's no guarantee. Do you see what I mean? If they are the same, it's just accidental. There's no mathematical guarantee that they should be the same. Okay? Good. Other questions before we move on? Interesting questions? Is that okay? So far, so good? Okay. If you have questions, you may hold on to it until the end of this class, and then you can ask again. So in the meantime, let me motivate what we are going to do in the module of physics of atoms. As I introduced in the first meeting, our course is much like a course about the physics of matter. By matter, we mean atoms, molecules, solids, or even nuclei. So now we are ready to start our journey into the physics of atoms. A reason that we start our journey here is that you learn the hydrogen atom physics quite well in quantum mechanics 1. You know the exact form, you have all these eigenfunctions, you know how to do the eigenvalues, etc., right? So that will be a good background because we need an unperturbed problem, the H0 problem. And you know that, okay? We have all this picture. I saw that in your notes last term, you have colorful picture of the P state, D state, all this thing. That is nice. That will be used for bonding in molecules later. So that is a good place to start our discussion. We will do two parts in the physics of atoms. Part one, we will try to stick the discussion to hydrogen atom by adding in many effects not considered previously. The first thing we will do is Zeeman effect, meaning I add an external magnetic field to the atom and see what happened, especially what happened to its spectral lines, the spectrum. Right? But in order to understand what happens to the spectral lines, we need to understand what happened to the energy eigenstates of the hydrogen atom in the presence of an external magnetic field. So that is the first thing we would like to look into. Then there is something very interesting that happens experimentally, even without an applied external field. That is to say, you don't need to buy a magnet, but it's always there. It looks as if, even if you don't apply an external magnetic field, there is an internal magnetic field. You can imagine that due to the orbital motion, if you think about Bohr model, you have the 1s orbit, okay, other thing, then electron orbiting is like a current loop. Therefore, it will generate a magnetic field. So there may be an internal field that could cause some effect, and that is called spin-orbit interaction. That's nice. You have learned orbital angular momentum last term, and you have learned spin last term. Here is the part in which these two things coupled. And then the observable effect is called fine structure in the hydrogen spectrum. Okay, we will discuss that. Then, since we have spin, we have orbital angular momentum, this will lead us to discuss something called the total angular momentum. Have you done anything about total angular momentum last term? Something called J. Okay, I looked at the notes yesterday. I didn't find it, but I don't know whether in lectures you have that. Okay, don't worry, we have to introduce that. Therefore, we will have some general discussion on angular momentum in quantum mechanics. All this hydrogen effect at the end, we will also discuss a little bit about something called hyperfine structure, which turns out to be what the astrophysicists are trying to survey the sky, or how one get this beautiful picture of a spiral galaxy. They are measuring some spectral line signals from the hydrogen atoms out there. Okay, in the vast space in the universe, and using that signal together with Doppler's effect, you can reconstruct that this part of the galaxy is moving out from us, the spiral go this way, some is going into us, so you see all these wonderful and beautiful pictures. All this discussion will be done in the background of hydrogen atom, because we have some knowledge on it. But the discussion is general in the sense that we could include spin-orbit interaction into lithium atom, into carbon, into silicon, into all the other atoms. They are there. In fact, the heavier atom, it is more important. But the easiest way to see the physics is within the context of hydrogen, okay? That's why we will do some additional terms to hydrogen in part 1. The next part, part 2, in this module, will deal with all the other atoms. How to do helium, that is not doable. I mean, cannot be solved exactly. Then we need to introduce further approximations at that point. But that has to do with approximations in a slightly different sense than what we just did. We have to try to approximate many electron problems by single electron problems. Okay, so how to mimic electron-electron interaction by thinking about one electron living in an environment that the second electron is doing something on you. That is called mean field theory. So we will discuss the idea. The mathematics is harder, and we will not do much mathematics on that, but I would like to introduce the idea so that some of you move into more serious quantum chemistry or computational material science research, you know what these ideas are about. Then we cannot avoid the problem of handling many electron wave function. Hydrogen is single electron, we can avoid how to write a 2 electron wave function, for example, but now we cannot. So we'll have to introduce some rather interesting idea. The electron wave function must be antisymmetric. There is a symmetry requirement. And then at the end, we will try to make sense out of the periodic table. So that is our plan. 2 parts. So let's kick off part 1 with a motivation. And this also try to write down the most important assumed knowledge of a hydrogen atom so that we have some common ground to move on in part 1. First question, we solve, well, you solve, I didn't last term. You solved this hydrogen Schrödinger equation last term. The question I would like to address now is, does it work? Does it really work? On the way, I would like to remind you what the problem was and then what is the solution. The hydrogen atom in the most basic form, meaning no spin-orbit interaction, no external field, nothing, okay? This is the bare or the 99% of hydrogen atom problem. You have this Schrödinger equation. This is a 3-dimensional problem. The nucleus is assumed at 0, 0, 0. That's why you have the R. Actually, this M should be replaced by the reduced mass to be correct. Nonetheless, we use M here for the moment. Okay, you solve this. Then this falls into a class of problem called central force problems. I know that you had a chapter on this kind of problem last term. And to me, I will often call this problem U of R problems, or spherically symmetric potential energy function problems. Okay, So this will be my description of this kind of problem. For the reason, in quantum mechanics, we usually care more about what is the potential energy function that comes in here. You see my symbol there, okay? We don't talk much about force, although that means central force problem. In classical mechanics, that is the chapter. But in quantum mechanics, it is more direct to address this type of problem as a U function here, potential energy function, that depends only on the radial distance from the origin, the R. That means there's no theta and phi dependence in U. And that is what I meant by spherically symmetrical. From the origin, you go out in any direction, the same R, the same U, okay? An important idea, it doesn't mean that the wave function also follow this. The wave function has very interesting directional dependence. You see that, right? Px, Py, Pz, directional, okay? But the potential is spherically symmetrical. When you do that, you can apply, because of this property, you can apply separation of variables. And then you can do the theta phi separately. They are called spherical harmonics. And they are good for all U of R problems. Doesn't matter, it's hydrogen atom, it's a harmonic oscillator 3D, doesn't matter, okay? It's always there. Then you have a radial part of the wave function. That really depends on what is the form of this U of R. For hydrogen, you pick up a special function called Lagrange polynomials. The energy of hydrogen atom is very particular. It only depends on N, not even depends on L. In general form, any U of R, the energy depends on N and L. That is general U of R, but hydrogen, you have accidental degeneracy, you have higher degeneracy by accident of this Coulomb form. And the energy is given by this famous minus 13.6 divided by N squared eV. Actually, this 13.6 is a combination of charge, mass of the electron, h bar, epsilon 0, all the constants. So in a pictorial way, the energies is given by discrete values, minus 13.6 divided by N squared, N is 1, 2, 3 here, and all the eigenstates are listed here using their N, 1, 2, 3, and L. In atomic physics, L equals 0 is S state, L equals 1 is P state, L equals 2 are D states, okay? And in hydrogen atom bare model, this one, all of them have the same energy, so they're higher energy, a higher degeneracy than expected from U of R alone. By that I mean, if it were only U of R alone, we have energy being E, depends on N and L. Okay? But now in hydrogen, accidentally, it's not even depending on L. It only depends on N. Okay, that is a very special thing about the Coulomb form, this one. So the question next is, does it work? This is actually part of the last week's exercise class. I will show you some data, high precision data from spectroscopy, 光谱学, that is the very accurate experiment. Okay, so but before showing you the table, you better know the language that is used in the data books. So the language they use is wave number, 1/lambda. What does it mean? Okay, so in physics, we usually use electron volt, we use frequency per second, we use angular frequency. H nu is the energy of the photon, h bar omega is the energy of the photon, okay? And for light EM waves, that is, C is F lambda. That is what physics students learn. But in data book, very often you see this wave number stuff, centimeter inverse. Oh, it's not EV, it's not Hertz, it's not per second, it's not, that's troublesome, right? So what does it mean? It's easier than you thought, I think. Wave number 1/lambda, look at the unit, centimeter inverse. So it's some number per centimeter. What does it mean? How many wavelengths are there per centimeter? This is what it means. Okay, so again, it's talking about lambda. You have the constant C, that is to say, it's talking about frequency. It's talking about what we used to talk about, but in a funny way. All right. So now, understanding this, then you can work things out. An example is given here: visible light. High school, you learn about this, right? 400 to 700 nanometer wavelengths, right? But for this one, near red, okay, the wave number is 10,000, okay, 15,000 wave number, okay? So 15,000 wavelengths per centimeter, that is the ballpark of visible thing, okay? So get a sense. Usually this symbol is used for 1/lambda, that is the wave number. Then we know that in spectral lines, there is a transition from one allowed energy of an atom to another allowed energy. Those are the solution to the Schrödinger equation. So you have E higher, E lower, the delta E, okay? It is given out as photon energy, but this is not data book gives you. Data book gives you this. So how could you relate it to our more comfortable thing? It is something like this, okay? So you have the delta E in terms of EV, usually H nu. Then actually it is what that is divided by HC, two constants. Then you get what data book says, right? So now I show you what the US Standards Institute of Standards and Technology, 標準局, 標準署, okay? They keep all the time the most updated precision spectral lines data for all the elements. You can go in there. I give you the link in the sample question last week. You click it in, click your favorite element, you see a list, okay? So here I took the hydrogen atom one. You see all these more familiar labels. And then you see a 0 here. So it is set to be 0. That is the lowest state, 1s state, okay? And now you see there's something called the limit. You can think about it, that is the ionized one, set free the electron. And you see something funny thing, 109,678. And that is given in wave number, all right? But now we understand. it is a representation of the energy. Okay, so it's saying 1s is here. If you ionize it, it takes that much wave number. You can convert it to energy. Okay, so you see that you convert it, divide, using HC converted. This is something like 13.6 EV. Pretty nice. Okay, so that is to say what you learned last term works. Okay, you see it's not quite right. Don't worry, you plug in the reduced mass, you can get it closer. But more interestingly, read this thing. What you get last term, is the 2s and 2p. They should take on the same energy. Degenerate. Okay, 8 states, including spin. Look at this number, 82258, almost 82259. Okay, so if you are not looking for high precision, 82259 wave number, these three numbers almost the same. So what you learned last term is 99.9% okay, right? But if you are curious enough, not quite exactly the same. So if I draw it out for you, okay, I copy this number out and draw it in the usual way. So 0, I draw it 1s down here, and then n equals 2, the 2, 1. I have 3 numbers. I have this one, okay, and then I have this one, that is a P, and then I have another P, okay? So I draw it here, it's slightly higher. There's a P that's lower, slightly lower, but this is not to scale. What do I mean by that? Now this is 0, this is 82,000, and I'm off by 0.1, so I shouldn't draw it out. I can't draw it out on this scale, but just to make the point, okay? So you see how Schrödinger equation works so well, okay? We are off by, I don't know, 0.001% accuracy, okay? But indeed, there are some difference. Then the question is, what are they? They are called the fine structure. There's no external field, but the difference are there, okay? And that will be one question that we want to look for the answer, okay? So we have questions to ask then. We have things to do. How can we account for this difference? One big part has to do with spin-orbit interaction, okay? And relativistic correction will also contribute a little bit, all right? Then we will try to explain the big part of this tiny difference. You may wonder, what for? Sometimes I also wonder, what for, okay? But if you know spin-orbit interaction, when you are handling solid-state problem, in recent 5 years, spin-orbit interaction turns out to be a very hot research area. Again, it's a cheap way. You don't need to buy a magnet and you have a magnetic field. Okay, nice. So I will stop here today. Then next time, we will start our journey into understanding more about hydrogen atom and then all the other atoms. Okay, so sorry for the technical problem at the beginning. Nonetheless, we have done what we want to do today. Okay, so bye-bye for now. See you on Thursday.